Hello everyone. I hope you are doing well. And recently, I posted many contest solutions, and you really showed the love and watched the videos completely. And I loved your comments, right? You did comments, and do keep doing that. I will read that and will reply as soon as possible, right? And also, I'm very happy my channel is growing good. So keep liking the videos, keep subscribing, and keep. If you're new to the channel, we are highly motivated and making awesome content around DSA tech and dev. So if you want to learn something about that in a very innovative way, you can subscribe this channel and also share with your friends. Now, this question recently came in the contest, weekly contest. It's a hard problem, but it's not. It's like literally medium. It's a medium. If you say about standard things and then knowing things, it's actually easy as well. Then you will be say, easy. What? You kidding me? Easy. Literally, it's hard written. Lead code is. Yes, it is actually. It's an easy problem. Literally, it's an easy problem. There's no difficulty. There's no difficulty at all. It's an easy problem. Sometimes it happens, right? When you see the problem, it's hard, and you think, oh, I cannot do hard. I can do only medium, and also medium get tricky sometimes, right? So no problem. We'll see and deep dive into it. That how can you think about the problem, and I will remove your fear from the heart. That's my overall motive. Right. So what does this problem say? You're given with array integer array nums. Fine. A subsequence is stable if does not contain three consecutive element. Same parity when the subsequence is read in order consecutive inside the subsequence. Return the number of stable subsequences and 10 power. I hope whenever you see this kind of things, right, 10 power minus power 7, you should think about at least two things. Remember that always, always, always it's gonna happen. Like either it will be a PNC problem. PNC means permutations and combinations problem, or means a math problem. Either it is a recursion problem, and recursion without DP and with DP. Only these possible things is possible. Other than that, there's not at all chance that this could be solved anyway. Binary search could be there, but it's very less chances. These are the most probable chances should have. And firstly, you should think about always this case. Recursion with the DP. Always, always. Path counting, something like subsequence. Always think about that. So I gave you a good hint about that. Okay. Fine. Fine. Then what's next? Let's understand the question first. It says that without reading the question itself, we derive this. So we will think about this and keep going forward, right? 135. So let's try to convert into parities, right? They are talking about only parities. The parities are nothing but even odd parities, 111. And then what they want is you want to create and calculate the number of subsequences such that they if you make a subsequence and there should not be three consecutive same parity bits. Either should it cannot be at 000, it could be 111, it should not be there. And not only that, their extension should also not be there, like one, like suppose this is also not valid. Why? Because this already contains this, right? So what does it say? That when a subsequence is read in order, three consecutive elements, not only this should be omitted, this also completely should be omitted. One, whatever random comes after it, all will be omitted because this is not correct. Firstly, let's try to understand the problem. I hope you understood the problem very well and I was able to explain you the problem. Now let's try to think and deep dive how can you solve the problem. What things come to your mind? Oh, something like can we calculate number of bits or number of odd numbers on left side and number of odd numbers on right side, and can we do something? You can do something, but there will be overlaps. How would you deal with overlaps? That's the primary question. Like I initially thought of an idea that let's say I had the current index I, and then let's say I just calculate till ith index, I how many subsequence I can make. Ending at I thought that would be a unique approach, but it turns out it is not. It is not, because you can calculate and maybe pick some of the elements. I made the drawn the cases, pick some of the elements, pick some of elements here such that they should not be consecutive. But the problem lies in the fact that It's not like you're picking only elements. It's like, how would I explain? See, let me just explain you how it is that does that fails. So let me just give you a simple example of that thing. What was our that example? It is like 2, 3, 4, and 2. Okay. So let's convert into the parity array. Should be 0, should be 1, it should be 0, and it should be 0, right? And then what we gonna do? We gonna calculate that how many subsequences ending at this particular index, like each index, and can we calculate the answers? For ending at 0th index, there how many subsequences are there? 1. Fine. Ending at 1, how many subsequences are there? uh 2, right? 1 itself, and then 0, 1, so you can say 2. Now ending at 3, how many subsequences are there? It's 0, it's 1, and then you can pick any subsequence, right? So it would be all the total 7 we have. Now let's try to think here. When you come here, how many subsequence you can calculate? So you will be like, this is 0, I cannot pick two zeros before that. Okay, I cannot pick two zeros before that. So okay, then I pick here 0, and let's say I will calculate what, how many elements are there before, how many frequency of elements are 0 as there. So there is two zeros here. Fine, there are two zeros here, right? And then what are you gonna do? Maybe this is there, then you're gonna do some math and you will figure out it's very difficult that to calculate every step. I thought this approach, I struggled a bit, but eventually I left this approach, that it won't gonna work. For some test cases, it was giving some wrong answers, that how can I be very sure that at which step how many things I can do. Because the fact is that you cannot calculate just numbers. See, this is a valid thing, this is a valid thing. It's not about only numbers. I was in focused on only numbers, and numbers, it's not like I was thinking, oh, I just calculate the number of two, should there should be less than two zeros uh, on the previous side, like this. But I didn't think of this example that this is valid. I was not counting that. So yeah, this approach won't work. Okay, then we are back to the zero. Oh, our approach shatters. Don't worry. Then we'll move ahead. How will we move ahead? See, what is this? It's very simple, yeah. Try to think. You are at ith index. What you need, what you just know about. You should know about the last parity, whatever you have picked, and how many consecutive you have. Right? This only the three information you need. Right? You need the last parity, what element you have picked, your current index, and the consecutive, how many consecutive element of that parity you have picked. You will be like, yeah. Then in these kind of scenarios, you just calculate the complexity, that how much at max multiply all of them. That's how you calculate the dp time complexity, right? I could go up to n. The consecutive parity can go up to 2, 0, 1, 2, and it could be go up to 2. We'll see, it will actually go to 3, that, but yeah, you can say 0, 1 is a parity. Oh no, it's 4n. Oh, we can solve this. We can solve this. It's a DP thing. It's a DP thing. You should think now about DP. From here, we'll start with DP, and you will be like, fine. Then how would we go, and about how would we write the transitions? See, it's pretty simple. You are at a ith index. Now, again, it's a pick no pick problem. It's a pick no pick problem. Now, you can just define int pick equals to 0. When can you pick? You can pick be like, and let's try to first write the base cases. What are the base cases? So let's try to write the base cases. The first base case is if our whatever consecutive, or let's say I'm naming it count, becomes less than 0, means it is more than 2, will return a 0. That's not a valid path. Fine. When we will return, see, when you're calculating the number of paths, right, you will end at that index and you'll count from there. And if I equals to n, we're gonna return 1. Is this valid? Is this valid? It's not. Why? This is valid. Always it's valid. But this one extra case we are emitting, that when we don't pick anything. Pick anything. That case also we should have made, right? So we'll check that. I will tell you that how will I'll check that whether a particular element we haven't picked anything. How would we do that? Okay. So to do that, actually we'll use a trick. It's a very good trick and you should apply on other problems as well. So instead of sending, so tell me one thing. Then when you're sending initially that parity to your function recursive function, what will you send? Like what is your previous bit? It is zero or is it one? It's neither of that, right? We don't know. So that's why. And you cannot use zero or one, something like that. You should define it with minus one. Minus one signifies that it's not defined. It's we haven't picked any element yet. And that's how it will help us to solve this particular question. So use minus one as the previous parity actually. Previous parity. Fine. We're gonna return then zero. And then actually we'll check if previous parity should not be equals to minus 1. That means, yes, we can write it. Now let's try to write the transitions. Okay. Now, when can we pick? We are at ith index. Now we have two options. Either we pick, either we no pick. No pick, to no problem. What will be the transitions? Let's me the keep the name of the function, recursive functions to be solved. And there will be three states. I, the previous parity, and the count of consecutive. So I will go with I plus one. Previous parity remains previous parity. Either it's minus one, one or zero. I don't care. And count remains count. No thinking in no pick. Now in pick, there are two kind of scenarios. There could be two kind of scenarios. What are the two kind of scenarios? The current parity is equals to previous parity, and or they are not equal. When they are not equal, can you tell me what will happen to the solve function? It's simple, right? Right? Solve. You tell me. Write your own. Then you will understand it very, very better. I plus one, so you will anyway go. What will be your previous parity now? It will get changed, right? It's not equal, and you pick, and we are picking on the last parity. There will be nums of I, whatever is the current parity, it's nums of I modulo. And then it would be like count. Count would be one. Why one? We picked one element of this parity. This is one, right? So we already picked one element. So it should be one. We can pick one more element of this parity that at max. If in this case, what would be the thing? See, we already handle this case of count less than zero. So if somebody is worrying, oh, you're picking more than two, you're not putting that condition, it's not required. Why? Because I already handled that in the base case itself. It's an implementation thing you can do in anyways. So remains previous parity. And interestingly, my count decreases by one. That's the interesting. That's all, yeah. That's all. That's all. And that's all. And you just return skip plus no skip. Beautiful question. Standard question. Thought about many things. How we fails. Then we go to recursion. Right. I also made a recursion tree for you for better understanding. Like I myself made it in the copy for your better understanding. This is for 1, 3, and 5 array. So I this define the state like index, and this is like previous parity and the count. You can see that I made the tree. Okay, this is pick logic. This is no pick logic. No pick logic. Okay, so this is it's not visible. We just remove that. Should be like pick, and this is no pick. And we're gonna define on each recursion state, and you can see that these are the states repeated. That's how DP works, right? These are the states. You can already calculated that. Why you need to calculate it again? And then this is how this is and this state is invalid. I already told you. If we reach at somehow either there are two possible scenarios. Either our count becomes less than zero, that could be an early return state, or it could happen that when you reach the last end, it becomes minus, right? So that should not happen. In both the scenarios, you cannot do anything. Okay. So let's try to see. Let's try to see what you can do. See from here. You can understand that, right? Actually, this state is not possible. From here, you cannot go. Count becomes zero. And then if you pick again, it's not possible. So you will return zero from here. Return zero from here. That's it. And other state, you will return one, 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 one. And you get six as the answer. It's a beautiful question, right? Let me just move quickly to the solution. Also, this is two, three things I will also tell you that you should be careful about. So first thing is you create a DP of n, the index, the parity. That it does not matter. You can interchange the parity thing and the count thing. So three size, by three size, parity is of -1, 0, and 1, three states. Count is 0, 1, and 2, three states. Right? Now you cannot represent -1. I hope you understand that. You cannot represent -1. So you will do another trick. We'll do a previous parity plus one everywhere. I hope you know this trick. You must have solved these kind of tricks, but it's very useful. So when you're returning also, when you're storing the states, actually will treat as -1 as 0, 0 as 1, and 1 as 2. It's just a notation, right? It's just in our head. What is the previous parity? We are just checking the values. We're comparing only. It does not matter, right? So that's how it's very, very important that you can do that. And then you just gonna calculate this, gonna store that state. And I hope this is particularly fine for you guys. And do let me know that if you understood the problem very well or not. Okay. So yes, so how are we gonna do about it? This is our base case. This is our base case. This is I wrote the thing. Then if you are at n, then if you are previous priority -1, that means you have to return 0, else I return 1. This is a DP memoized state. Then you can check in the current priority with the previous priority, right? You're checking with the previous. Acha, note that this parity is we are sending previous parity only. But when we are storing this it plus one. So don't confuse that. Okay, when we are storing, we're comparing with -1, 0, and 1 only. Don't worry about that. Okay. And we are just storing is an in this way because we cannot store -1, right? So, and then we wrote the pick two conditions that if it is same, then you can gonna -1 and then gonna do a same previous parity continues. Elsewise, you start a new parity of the current parity, I plus 1 and assumption DP, and then you can skip it, very simple logic, and then you want to do a mod as well. Don't forget to put a mod because it's at power -7, and also it can overflow it. So always do with a long int. You can do other things as well, but I found it very convenient. Just define everything in long int. No overflow will happen. You just do a mod every time, and yeah, it's you will be able to solve this particular problem. So I thought this problem is very interesting. It's a standard problem, easy problem. I hope you understood the solution as well. It's same skip knapsack problem, pick no pick logic. We understood the entire recursion. We understood the entire intuition. And if you like the video, do hit the subscribe button. And I will be coming with more awesome content like this. And stay tuned. And we also started a new series of DP. If you're struggling with DP, I've made a complete series on DP that you can practice. And the link will be in the description. Do check it out. See you in the next video. Bye bye, guys.